Namaste and welcome to yet another lecture on mathematical foundations for machine learning. We have been looking at the idea of least squared solutions, and from the perspective of finding the best approximate of the B vector in the column space of A when B is not in the column space of A. Of course, we know that if B is in the column space of A, the best approximate of B in the column space of A is B itself. When it is not there, then we figured out in the last class that we need to get the orthogonal projection of B onto the column space of A, and then try to solve for A x optimal is equal to B hat, where B hat is nothing but the projection of B onto the column space of A. And when we concluded the last lecture, we had this question saying, look, where do we use this? And one of the most important problems, one of the most important ideas in machine learning is basically fitting a straight line, or let us say linear regression, right. We want to fit a straight line, we have collected data and we wanted to fit a straight line such that, I mean, if all the points are on the line, then that is the best that you can get, but with the amount of data that we have, it need not necessarily be true always that you have one single straight line which passes through all the points. Therefore, you need to find out the line of best fit. Let us take a simple example and see like how it goes, and then we further go ahead with this idea of pseudo inverse. As I said in the last class, we will come back to this idea once again when we do optimization, where we will look at the matrix derivative perspective. Like we know that we have functions whose derivative can be taken, continuous functions, if the derivative exists you can always differentiate the function and all those things, but we can also look at the derivatives of matrices and stuff, which we will look at a later point of time, like week 10. Then we will be able to understand much better. We will see that whatever we have seen here right now is what will come, the same result is what you are going to get even if you are going to do your calculus way or taking derivatives and stuff, right. So what we will do is just take an example right now and see like how it goes. Okay, so let us start. Suppose I have this, I have Ax equal to B, where I say that look, let us take this, I have a set of points, say 1 1, then let me say I have another point, let us say 1 2, and the third point which is let us say 0 1, or let me put this as minus 1, so that right 1 1, 1 minus 1 and 0 1. Now what we want to do is we want to look at can we find a fixed straight line which passes through this point. So let us look at that. Let us first of all draw this, mark these set of points on the xy plane and see if we can actually get a straight line passing through all these points. So what are the points? We have x1 and we have the x2 axis. I have let us say 1 1 2 3 4, and I have 1 2 3 4, then minus 1 minus 2 and so on. So I have 0 1 2 3 4 1 2 3 4 minus 1 minus 2 and so on. So the first point that I have is 1 comma 1, here is the point. The second point that I have is 0 comma 1, oh that is here, and the third point that I have is 1 comma minus 1, and that point is basically here. Now we see that there is no way we can get a straight line which passes through all these 3 points, right. So if we say I mean if we actually want to put it we want to find out a straight line, that means you know that a straight line is basically characterized by the slope and intercept. So we have let us say x2 is equal to c plus mx1. Normally write this as y equal to mx plus c. So what I have done is I have written it as x2 is equal to c plus mx1. Now the pairs of values that you have are basically x1 x2, right, in that order. So what I am going to do is I am going to take this x2 is equal to 1, which is equal to c plus m into 1, and then I have x2 is equal to minus 1, which is equal to c plus m into 1, and then I have x2 is equal to 0, which is equal to c sorry x2 is equal to 1 and c is equal to c plus m into 0, right. Now here if you see, we have equations of this form where the vector, if you want to write it in the vector format, the column format, I have 1 minus 1 1 is equal to c into 1 1 1 plus m into 1 1 0. Now it is interesting, if you see from the last expression you get c is equal to 1. When you substitute c is equal to 1 in the previous expression, you get the one that goes there. So m into 1 is equal to minus 2, so m is equal to minus 2 and c is equal to 1. So let us do this. This implies c is equal to 1, this implies m is equal to minus 2, and now you substitute it there, we have 1 is equal to 1 plus 2 into minus 1, which is not going to happen at all. This is wrong, right. We get a minus 1 there, but this is some kind of inconsistency that we have here. So the question is, you cannot find, there exists no c and m such that the vector 1 minus 1 1 can be expressed as a linear combination of 1 1 1 and 1 1 0, right. That is what we understand from here. So let us check once again. From here, from the last expression, I have c plus m into 0. So I get c is equal to 1 here, and I substitute that 1 there. So this 1 goes here, becomes minus 2, therefore m is equal to minus 2. Now when I substitute minus 2 into 1 plus 1, you should get a minus 1, but you end up getting a plus 1 on the left hand side, which means this is inconsistent system that I have, right. This simply means that in 3 dimensional space, because these are 3 component vectors. So what we have is so we have our vector space to be equal to R3. In that we have a 2 dimensional subspace, we have a 2D subspace, 2D subspace W spanned by the vectors 1 1 1, 1 1 1 and what was the other vector, we have 1 1 0. Now you can very clearly see that 1 1 1 and 1 1 0 are basically 2 linearly independent vectors. In one case you have the third component to be 1 and the other case you have third component to be 0, therefore they are linearly independent, and therefore the subspace spanned will be a 2 dimensional subspace by these 2 vectors. Therefore, and what we see is the vector the vector 1 minus 1 1 does not belong to the column space of A, belong to the subspace spanned by one 1 1 and 1 1 0. That means the vector B does not belong to W, W is the subspace, right, it does not belong to W. Now what do we have, what do we do in this case? We want to fit a straight line, this vector does not belong to the subspace. Now we know what is the trick that we need to do. So what is the trick? We just need to find out what is A transpose A, the whole inverse into A transpose, and then we will find out x optimal is equal to A transpose A the whole inverse into A transpose B, where x optimal is basically these two values, let us say m hat and c hat and m hat, or let us say c dagger and m dagger, because these are not the actual m and c that you can get. You will actually get something, there is no actual c and m value which would do this, therefore I am looking for an approximate to b, therefore I will call this also as c dagger and m dagger, right. Okay, so what is A transpose A in the first place? What is A transpose A? First of all, let us figure out what the matrix A is. The matrix A is 1 1 1 1 1 0, right. Therefore, what is A transpose A? So, A transpose A is equal to this 1 1 1 1 1 0 into 1 1 1 1 1 0. So, that is going to give me, so this is 1 into 1 plus 1 into 1 plus 1 into 1. So, this is going to be 3, then I am going to have 1 into 1 plus 1 into 1, which is 2, again 2, and then I have a 2. So, A transpose A is 3 2 2 2, and A transpose A the whole inverse is basically the adjoint of A transpose A divided by the determinant of A. This is nothing but adjoint of A transpose A the whole A transpose A divided by determinant of A transpose A, and the adjoint of A transpose A, this is a 2 by 2 matrix. So, all we need to do is change the swap the diagonal elements and then change the sign of the off diagonal element. So, you are going to have this divided by the determinant is nothing but 6 minus 4, which is 2. So, this is nothing but half of 2 minus 2 2 3. So, this is what we have. Now, what we are going to do is we found out A transpose A the whole inverse. So, I want to figure out what is A transpose A the whole inverse into A transpose, that is nothing but half into 2 minus 2 minus 2 3 and into 1 1 1 1 1 0. So, that is going to give me this is half of, let us take this 2 minus 2 0 2 minus 2 0 2 into 1 is 2 minus 2 plus 3 is 1 minus 2 plus 3 is 1, and then you have a minus 2. So, A transpose A the whole inverse into A transpose is nothing but 0 0 1 1 by 2 1 by 2 and minus 1. Now, recall our B was this, the B that we were looking at was 1 1 1 minus 1 1. So, this is what we have. So, I am now going to evaluate A transpose A the whole inverse A transpose into B, which is nothing but 0 0 1 1 by 2 1 by 2 minus 1, and that I am going to multiply with my B. B is nothing but 1 minus 1 1. This is what we had, right. This is the B that we had. So, if you look at it, this is going to be 0 into 1 plus 0 into 1 minus 1 plus 1 into 1. So, I am going to get, which is 1 here, and then I have half minus 1. So, this is what I have. So, what do we get? We get the x dagger, which is the optimal solution, is basically 1 minus 1. Recall we had the equation of the line, recall we had the equation of line to be y is equal to mx plus c, and we or we had c plus mx. So, y is equal to c plus mx, this is what we had. Now, what we see here, we found the value of m and c, the value of m is minus 1, the value of c is 1. So, from here we can say that C x opt, basically the components of x opt or basic or the x dagger, which we also call it as the x opt, the optimal solution, is given by basically C and M, and that here is nothing but 1 minus 1. Therefore, our line of best fit in this case is going to be line of best fit is going to be y hat is equal to mx plus c or c plus mx. I will put it that way, which is nothing but c is 1 and minus 1 plus minus 1 into x. So, this is going to be 1 minus x. So, we have y hat is equal to 1 minus x, right. Now, what we will do is we will figure out what is this y hat. Our given y was basically this. What was the given y? We had 1 minus 1 1. Now, y hat, what we will do is we will substitute the values of x that we had taken. So, y hat is nothing but 1 minus x, where the values of x that we considered was 1 1 and 0. X was equal to 1 1 and 0. This is what we had, right. You can quickly check that out. So, the equations are 1 1 and 0. So, we have x 1 x 2. So, we have x 2 hat here. We will, since we have taken x 1 x 2, we will take x 2 hat is equal to 1 minus x 1 hat. So, we have this. The given x 2 vector was basically 1 minus 1 1, and what we have here is basically the x 2 hat is given by 1 minus x 1. So, what are the values? We took x is equal to 1. So, x 2 hat is going to be, when x 1 is equal to 1, 1 minus 1 is 0, then 1 minus 1 is 0, then 1 minus 0 is 1. So, this is going to be my x 2 hat. Now, what we want to do is we want to figure out what is the error that we have in the squared error. So, what I am going to do, I am going to take my x 2 minus x 2 hat. I am going to look at the squared norm of this, then we will see what happens. So, I am going to have x 2 is nothing but 1 minus 1 1, and then x 2 hat is nothing but 0 0 and a 1. So, this is what we had. So, which is nothing, and I want to look at the squared norm of this. So, this is going to be 1 minus 0 is 1, minus 1 minus 0 is minus 1, and 1 minus 1 is 0. So, this is what we have, right. So, the squared distance is going to be square root of, so the squared norm, squared error is going to be square root of 1 squared plus minus 1 squared plus 0, which is nothing but square root of 1 plus 1, which is square root of 2, right. This is what we have. I have substituted the values of x 2 hat, which is basically obtained using y is equal, y hat is equal, or x 2 hat is equal to 1 minus x 1. So, we have substituted this, and this is the value that we get. So, what do we understand from it? So, this is going to be the what would I call, this is going to be the smallest squared error that you can get, with the coefficient, the intercept being 1 and the slope being minus 1. So, the length, the squared length is going to be root 2. So, the length of the error vector. So, the length, this is the squared error, which is 1 square plus 1 square, which is 2. So, what do we have? The length is going to be, the length of the error vector is going to be square root of 1 plus 1, which is basically root 2, right. Now, this is interesting because this is the smallest squared error that you can get. You put any other x, the values of x, the values for x 1 across this in this expression, c plus mx is equal to y hat. You put any other values of x in different values of x and then collect the vectors, you are going to get a different length, which is going to be larger than the square root of 2. So, that is more important. So, the what we get is the line of best fit in this case has the, okay, let us write this, the line of best fit has slope is equal to minus 1 and intercept is equal to y intercept is equal to 1. Therefore, the whatever we have found out, the x dagger, which we will also call as the x opt or the optimal solution, is going to be Cm, which is equal to 1 minus 1, right. This is what we have. Now, let us look at another question. What is that? So, suppose we have this. So, the question basically here is, suppose A is a wide matrix. In this case, we took A to be a tall matrix. Now, what we will do is we will take A to be a wide matrix, right. Let us say A m by n, where the number of rows is less than the number of variables, and what we are going to do is we are going to take the rank of A to be equal to m, the rank of A to be equal to m, right. Let us consider a simple example. In this case, we are going to look at this example. We say A is a 2 by 3 matrix of rank 2 of rank 2. Now, what does this mean? I have a 2 by 3 matrix which is of this form: A11, A12, A13, then A21, A22, A23. Now, this is basically a matrix of 3 columns of 2 component vectors, and we have already said that the rank is 2. Therefore, what we are going to do is we are going to take that there are 2 linear, this means that there are 2 linearly independent vectors, or there are 2 linearly independent columns in the matrix A, which means the column space, of R A, column space of A is basically R2. Now, what do we mean by that? We see that, look, we have, you take of these 3 vectors either A11 and the first column and the second column to be linearly independent. Therefore, the third column is naturally a combination of the first 2 columns, or if you take the second column and third column to be linearly independent, then the first column is going to be a combination of the second and third column, or you take first and third column to be linearly independent, then the second column is going to be a combination of the first and third column. That means you are going to have 2 linearly independent vectors, and we know that if you have 2 linearly independent vectors, it will span a subspace of 2 dimension, or it will span a 2 dimensional subspace. Therefore, in this case what you are going to say is, we say that the column space of A is basically column space of A is a 2D subspace of A is 2D subspace of R2, but in this case this 2D subspace of R2 is basically the R2 itself. Now, what we do is we will see what happens when we have such a case, like how do we compute the pseudo inverse. So, what is Ax equal to B mean? What does Ax equal to B imply here? This implies I have x1 into the first column of A plus x2 into the second column of A plus x3 into the third column of A is equal to the right hand side vector B. Now, we already said, in at least in this case of this 2 dimensional subspace example that we have taken, where we have 2 component vectors and stuff, what we know is B is also going to be a 2 component vector. We already know that there are 2 vectors which are linearly independent. Therefore, this B being a 2 component vector would still remain in the same column space of A. It is not going to be out of the column space of A. Why? Because that is a 2 component vector and the rank of this matrix is 2, and therefore B vector is going to be there in the column space of A. Therefore, this I do not have to project this B onto the column space of A because that guy is already there. Therefore, what do I do, right? If you look at A transpose A in this case, A transpose A is basically a 3 by 3 matrix, 3 by 3 matrix of rank 2, which implies A transpose A is not invertible. Right. But what we know is if you look at A transpose, A transpose is a 2 by 2 matrix of rank 2. And A transpose is invertible. In this case, note that B is already in the column space of A, in the column space of A. Therefore, the matrix which projects, the matrix that projects B onto the column space of A is the identity matrix. Column space of A is I 2 by 2, the identity matrix, 2 by 2 identity matrix. Right, this is going to be the 2 by 2 identity matrix itself. Now, we know that A transpose is invertible, therefore, I can say that look A transpose inverse exists. Therefore, what we have is we know that A transpose into A transpose inverse is equal to the identity matrix, which means I am going to have A into A transpose into A transpose the whole inverse is equal to identity matrix, and this identity matrix is basically the matrix which projects. This is exactly what we had in the previous case. If you want, we can recollect that. What we will do is we will just recollect this. We will say in the previous case with A m by n, case A m by n, rank is equal to n, we had A into A transpose A the whole inverse, A transpose is the matrix that was projecting, right, is the matrix, oh sorry, A into A transpose A the whole inverse, sorry, A transpose, this was basically the matrix which projects, this is the matrix P that projects B onto the column space of A. Right. In this case, in the current scenario where we have, in the present case, in the current case, and we call this here as A pseudo inverse, right. In the current case we have A m by n, rank is equal to m, and we figured out that A into A transpose into A transpose the whole inverse is equal to the identity matrix, exactly similar to what we have here. A into A pseudo inverse, A into A pseudo inverse was equal to projection matrix. Same way I have A into something is equal to the projection matrix, which is basically the identity matrix here. So, I have A transpose into A transpose the whole inverse, this is my pseudo inverse for A m by n with rank m. Right. This is basically the case where we have insufficient data, but we have more number of variables, right. So, if that is the case, then the pseudo inverse looks like this, right. When you have more amount of data, that means the columns of the matrix are, I mean, when you have the column all the columns of the matrix data matrix to be linearly independent, then you have the pseudo inverse to be A transpose A the whole inverse into A transpose, otherwise this is going to be the case. So, what we have seen in this lecture is basically we have looked at the idea of pseudo inverses, which will come very handy when we try to fit when you try to do regression. I mean you can even look at what do you call polynomial regression, all those things we would still be able to sort out all those things with this kind of the pseudo inverse and stuff. And essentially we will look back at a later stage of time, we will look at the same expression coming from the calculus perspective and so on. So, now from here where do we go? In the next class when we come back to listen to Dr. Ashok Rao, who will be starting off with singular value decomposition, one of the most beautiful ideas of linear algebra. So, he will do singular value decomposition, and then he will do principal component analysis, and he will do the support vector machine. So, these are lined up for the next 3 lectures of this week. Once this is done, we will end up looking at probability ideas. So, on that note, we will wind up this lecture. In the next lecture we will look at singular value decomposition. Namaste.